Okay, sorry for the long title. I know that you like shorter one, but okay. Let me first thank the organizers for organizing this beautiful conference, and also all of you for showing up. I mean, I know we are all tired. It's already the fourth day, maybe a little bit sleepy after lunch. So I prepared just a light talk about some project I just started. So it will be rather non-technical, but I think we have now a good framework which could help connecting various things, various areas. So let me start with the motivation. Okay, what is descriptive set theory? Well, classical descriptive set theory. According to Kekris, it is the study of definable sets in Polish spaces. Okay, this is the introduction of his book. And I guess that part of the success of descriptive set theory is that it applies to many, many spaces. I mean, Polish spaces are really a wide class, and Polish spaces can be found basically everywhere. Okay, here you have some examples, but of course there are many, many others. And therefore, once you develop a theory of the Polish spaces, immediately you have a toolbox for many, many situations, right? And okay, in the years there have been many attempts to generalize these to other spaces, okay? And usually the idea is you change a bit the class of spaces and see if you can still run a beautiful theory like classical descriptive set theory. And there are many, many approaches to this. I mean, many instantiations of this. I take three of them in chronological order. So the first one is from a paper by Stone. It's not Marshall Stone, it's Arthur Stone, a topologist from the UK. Who wrote a paper on so-called bare spaces. And for him, bare spaces were just countable products of discrete spaces, but of any size. Of course, if each space is of size omega, then it's a bare space. And this is the generalization is take spaces of any size. And it turns out that in any case, up to homomorphism, you're actually always dealing with the space of this form. He called this generalized bare space, which is lambda to the omega for some lambda, okay? For some maybe uncountable lambda. Why it is so? Well, because if in the sequence, infinitely many spaces have a certain maximal size lambda, then it's lambda to the omega. If lambda is of countable cofinality, you can do something different. You can take an increasing sequence and make the product of the lambda I, which is an increasing sequence. But it turns out by the work of Stone that this is exactly homomorphic to the other space if lambda is uncountable. So expect for lambda equal omega, which is the counter in the bare space, they are different. From omega 1 going on, they are just the same. So this is why I say this is the kind of spaces studied by Stone. Then there is another thing that I think the first occurrence of this is in a paper by Vo in '74. Then Meckler and Vannanen did a great job with the kappa equal omega 1 in this setup. And then I think in 2000 and something, people started really to work a lot on this. And the approach here is you take the counter space, 2 to the omega, and you replace omega with some other uncountable cardinal, 2 to the kappa. And you endow this with the bounded topology, which is the one described there. So you take just a bounded sequence and take any possible extension. This is a basic open set, and take the topology generated by this. I mean, this is the usual topology on the counter space, but just generalized to this uncountable cardinal. And let me point out that up to now, or at least mostly, the theory has been developed under this assumption, kappa to the minus kappa equal kappa. I really don't understand exactly, but surely most of the techniques that are used need this condition. So I would like to read this condition as kappa regular plus 2 to the less than kappa equal kappa, because it will be relevant for the rest. So essentially they are concentrated on regular cardinals. Notice that if you concentrate on regular cardinals, then you lose a lot from descriptive set theory, because this space 2 to the kappa is metrizable if and only if kappa is of countable cofinality, okay? So we are really in another situation where you don't have metrics, you don't have this kind of objects, and one has to devise new techniques. Okay, and now there are many, many papers on this subject. The theory is very, very interesting, with a lot of results going on, and but the result is that the theory is quite different from a classical case. At least in this regular situation, there are so many differences. I will tell a bit more later. Okay, and I was actually given a paper in this in this setup 2 years ago. And yeah, also Woodin suggested to look at the singular cardinal. This was an input I already had from Mirna and Jokovanen and many others. Why it could be interesting to concentrate on singular cardinals? Well, because they are beautiful, and because there are other situations where you can have still one, well, apparently different approach, but it's clearly the same. So this is the space V lambda plus 1, which is studied, for example, by Woodin in this paper, Suitable Standard Models. So the idea is that you put a topology in this way. You take V lambda, and then you decide some level, some alpha less than lambda, decide what the set should be up to this level lambda, and then take all the sets which up to level alpha coincide with that, and then they can do whatever they want, okay? And particularly, this study is performed under I0 lambda, okay? So this large cardinal axiom on this lambda.
Well, you wrote critical point.
Yeah, lambda is the critical point of iterate of that. Yeah, yeah, the critical point is lower. Okay. Okay, why it's reasonable to take this approach? Because in a sense, V lambda plus 1 is a large cardinal version of 2 to the omega. Okay, so if V lambda can be considered as an analog of V omega, lambda is a cardinal of countable cofinality. So if V omega is omega, then V lambda plus 1 is power set of V lambda, and in the countable case, power set of omega is 2 to the omega, okay? So V lambda plus 1, which is the power set of V lambda, is really an analog of the Cantor space.
But what is the analog of J? I'm always wondering when people start talking about this. There is no J, right, from omega to omega.
Yeah, no, I don't know. I'm just saying that possibly one can consider the extension because of that. I'm not going backwards. I'm not going from the large cardinal back to the classical case. I'm just going forward. Okay, of course, even the theory, again, is very, very rich with many, many beautiful results. As far as, I'm not an expert, but as far as I understood, the point is that the theory that you get for definable sets of this generalized situation under I0 lambda is somehow close to or reminiscent of the theory of L of R under AD. Well, with the exception, of course, it's not the same thing, there are exceptions, but many things goes on in a similar or parallel way. Okay, I presented these three approaches, but actually they are essentially the same, and the point is that if you just start, doing an exercise, in 5 minutes you realize that for singular cardinals, if you have the condition 2 to the less than lambda equal lambda, so if it is strong limit, I will discuss why I take this, then 2 to the lambda is the same as lambda to the cofinality, which is the same as the product of any cofinal sequence. Topologically, I mean, they are homomorphic, okay? And therefore, if you have countable cofinality, so if you are in the case in which mu is omega, what you get is just strong generalized Baire spaces. So B lambda or C lambda, they are all the same as 2 to the lambda. And also, in the case of I0, if lambda is big enough, for example, limit of inaccessible cardinals, then V lambda plus 1 is actually homomorphic to 2 to the lambda. So summing up everything together, all these approaches are actually studying exactly the same space, okay? So exactly topologically, they are studying exactly the space 2 to the lambda for various lambda, maybe singular, maybe irregular, depending on the approach, okay? So once you see this, the point is, okay, they are all dealing with this generalized Cantor space. Let me mention why I'm taking 2 to the less than lambda equal lambda, which is satisfied in all these approaches. Well, the point is that if you want to see this as a generalization of the classical descriptive set theory, in classical descriptive set theory, 2 to the omega is second countable, so it has a base of size omega. Here you want a base of size lambda, okay? And to get the 2 to the lambda as a base of size lambda, you need this condition. That's why it's there. I mean, there is a serious problem at the beginning if you don't assume that. You're studying some other space with a different weight, okay? So I will always systematically assume this condition. 2 to the less than lambda will be always lambda in any situation. Also, this is the generalized Cantor space, 2 to the lambda. One may wonder what is the generalized Baire space, so what is the generalization of omega to omega? Well, one option is lambda to the lambda, okay? This works fine in the regular case, there is no problem there. But if lambda is singular, if you do lambda to the lambda with the bounded topology, again, the base is too large because it's larger than lambda to the cofinality of lambda, which is larger than lambda, therefore the weight is too wide, okay, of the space. So the right choice you will see is to take lambda to the mu, where mu is the cofinality. Okay, so if it is singular, it's like a shorter space, and the height is just mu. If it's regular, it's the usual lambda to the lambda. Okay. Okay, so these were many approaches, and they are surely interesting. There are many, many results, and a lot of fun for us. But if you want to take this seriously, and you want to hope to mimic a little bit the subset of the classical descriptive set theory, I think we should care of finding the right setup where this generalized descriptive set theory works, because up now it works just for one space, 2 to the lambda. Okay, so if you want to apply this elsewhere, maybe there could be some problem because you are too specific on something that doesn't show up so much in the real mathematics, let's say. Okay, so this is the project I'm talking about. I'm taking this question. Is there a general notion, if I give you a lambda, is there a general notion of Polish space, Polish-like space, for which one can develop in a very general fashion, well, sort of generalized descriptive set theory, and I put there descent, meaning, of course, one can study any class of spaces. The point is that you want a class of spaces which works well, at least for the basic results, okay, the analog of the basic results. So this is what I'm going to talk about today. One of the cases we already considered, even if the paper is still unpublished, but it's, well, mostly written 1 year ago, is the case of countable cofinality. Okay, this was one case we studied exactly in connection with I0 lambda and this kind of stuff. So let me present what we got. You will see is exactly you know, a generalized version of classical descriptive set theory as basic results are concerned. So here we are working with an uncountable lambda, with countable cofinality, and with this condition 2 to the less than lambda equal lambda, so lambda strong limit, because of what I said. We want spaces of with weight lambda. And we try to just generalize the definition of lambda Polish. So we say that a space is lambda Polish if and only if it is still completely metrizable, as in the classical case, and but this time we allow the weight of the space, the base of the space, to be lambda. In this case, it makes sense to allow for complete metrizability because it is of countable cofinality. So 2 to the lambda is completely metrizable. Okay, there is no problem in having such a strong condition. Okay, then you go on and you just define naturally all the other concepts. So for example, you can define Borel sets. Of course, here will be lambda plus Borel set, meaning in the smallest lambda plus algebra. So you allow a union intersection of size lambda instead of countable. And lambda analytic sets, so here analytic usually, well, at least in Kekris, the first definition is image of some Polish space. So here, continuous image, of course. So here you can say continuous image of a lambda Polish space, but then you get automatically other equivalences. So for example, continuous images of the bare space, which I remind you is not lambda to the lambda, but lambda to the omega, is lambda to the cofinality, okay? Actually, the equivalence follows from some results which are on the next slide, but I mean, I'm sure you know how to prove them. It's just a bunch of observation. Okay, so first thing that we ask ourselves is how much closed is this class as a whole? If you take the class of all lambda Polish spaces, well, it is still closed under disjoint sums and now of size less or equal than lambda because the weight is lambda, so it's allowed to do this kind of union. But it's not closed under product of size lambda, okay? The point is that in the product somehow you have to take the cofinality. Here the cofinality is omega, and so the best you can do is countable products, essentially. And then it is closed under G delta subspaces just because if you have completely metrizable space, and these are, if you take a G delta subspace, it's still completely metrizable and vice versa, okay? So here we really mean G delta, so just countable intersection of open sets, okay? It's not lambda intersection of open sets. Okay, so these are just basic observations. The next thing that one can prove, it's very easy, is that if you take any lambda Polish space, then there is a continuous bijection from a closed set of lambda to the omega, this generalized bare space, onto this X. And the inverse of this injection is not continuous in general, depends on the space, but it is at least lambda plus Borel, so it's not too complicated. And then, of course, you can go on. If the space is non-empty, then you can extend this to a continuous surjection from the bare space onto X. And this is done just as in the classical case via retraction, because in this case you have retraction, I will mention later. And also, with a little bit of care, I mean, the strategy for the proof is the same, but one must be a little bit more careful. You can prove that the same results holds also for Borel subsets of X. If you take a Borel subset, you can find a continuous injection from a closed set of the bare space onto the Borel set. Okay? So if you see everything is like in the classical case, you have just to change what should be changed. Okay, what about perfectness? Yeah, of course, this must be changed a little bit. One can speak about isolated point as well, but what works well here is a slightly different notion. We say that in this context, a point is lambda isolated if it admits an open neighbor of size less than lambda. Okay? So isolated would be lambda equal omega, and here we generalize this omega to lambda, because essentially we are always replacing omega when possible with lambda. Okay? And then you define in the usual way perfectness. A space is perfect if it doesn't have lambda isolated points, and the subset is perfect if it is closed and perfect in the, as a subspace. Okay? And once you have this, one can prove exactly the same theorem as in the classical case. If you take any non-empty lambda Pauli space, which is also lambda perfect, then there is a closed subset which is homomorphic to the lambda. And let me mention, this is the first non-trivial result. Well, the other one were just a little bit technically tricky, but here you just need to use something different, okay? So first of all, the point is that we don't really embed 2 to the lambda, but something which is homomorphic, which is the product of the lambda I, where the lambda I is a cofinal sequence. So essentially, when you try to embed that space, you need to split many times cofinally in lambda. Okay, the first time at least lambda 0, the second time at least lambda 1, and so on and so forth, because it's large. Okay, and why can
Probably stupid question, but 2 to lambda is compact, right?
No, because it's on with the bounded topology, not with the product topology. Okay, actually 2 to the lambda is never compact. It is kappa Lindelof if and only if kappa is weakly compact. I mean, it's a bit different. Okay. So here we are in the situation in which all these spaces are the same, okay? So basically you choose the right one. The point here is that you cannot hope to do this embedding going for more than omega many steps, because the cardinal has countable cofinality. So maybe you reach the top and you can not go on, okay? So you just have omega many steps to do the embedding. So you take this space lambda product of the lambda I. The price you have to pay is that you have to split more, okay? Because you have to split lambda I time. And why can you do that? Well, because if you are in a metric space, you can, well, general fact in topology, but it can be proved by hand, that a space Y has a size less than lambda if and only if, has weight less than lambda, if and only if you can find arbitrarily large, well, even space sets. So these are discrete space of a certain special type with the metric, okay? But essentially these are discrete space which allow you to go on with the embedding to show that you can split how much you want when you do the embedding. And here it is crucial that we are working with uncountable cardinals. Such a thing cannot work in the countable case. Just because to have this equivalence, you need that kappa to the omega is less than lambda for every kappa less than lambda, which is guaranteed by 2 to the less than lambda equal lambda in our case. Okay, but this argument is really different from the classical case, as you see. I mean, it doesn't apply to the classical case. Okay, so we are getting the same picture. We can go on. We can decompose like Cantor Bendix on the composition of a space. If you have a lambda Pauli space, this can be uniquely decomposed into a perfect set and into a countable open, not countable, an open set of size less or equal than lambda. Now, countable is always lambda. Okay, so this is the usual decomposition, and P is called the lambda perfect kernel of X. And this can be done essentially in the same way as in the classical case. Either you take Cantor Bendix on derivatives, so eliminating isolated point, but lambda isolated point, and iterate in this process, or you can just take the lambda accumulation points defined in a natural way. This is already the perfect kernel. Okay, so this works perfectly like in the classical case. Combining the two results, we have this topological CH for lambda polyspace, which is the analog of what happens for polyspaces. So if you have a lambda polyspace, either it is small, of size at most lambda, or you can embed 2 to the lambda, the generalized Cantor space, into X as a closed set. Okay? So this is the kind of result I'm trying to keep. When I say this and descriptive set theory, I'm trying to keep all these basic results to work in general for my class of spaces. So, and this is the case. And also, if you combine this with the continuous injection we saw in the first slide, I mean, you do the usual thing, the Cantor-Schroeder-Bernstein theorem, topologically, you get that 2 lambda polyspaces are lambda plus Borel isomorphic if and only if they have the same sides. Okay? So actually, the 2 sides are either lambda or 2 to the lambda. There are no other sides. Okay, what about zero dimensionality? Okay, this was a little bit tricky because we start with zero dimensional in the usual sense, so having a base of consisting of Klopen sets, and this apparently doesn't work. We have to change to to move to another definition of zero dimensionality, and exactly we have to go with the Lebesgue covering dimension. So in particular, in dimension 0 means that every open cover of X has a refinement consisting of disjoint Klopen set. Okay? This is in general, well, examples are of course the generalized Cantor space and these other spaces, but let me point out that in general this is a bit stronger notion. Okay? For metrizable spaces, if you have dimension 0 in the sense of Lebesgue covering dimension, then you are also zero dimensional in the old sense. But if the space is separable, they coincide. But when the space is not separable, and this is our case, then the covering dimension can be higher than the other dimension. So it's a stronger notion. You have to impose that this higher dimension is still 0. Well, except for this, then you get the usual result. So for example, every lambda polyspace with dimension 0, in this sense, is a homomorphic to a closed subset of the bare space. Okay, this is another typical generalization. You have retraction, exactly as in the classical case, but with this definition of zero dimensional. Well, and all the consequences of this. I will not read the last one. Okay, so zero dimensionality works well if you take this other definition. Also, working a bit with this notion, there was a somewhat surprising result, which is the characterization of the Cantor space, which is simpler than the one you get in the classical case. Okay? Because you don't need compactness. Of course, this is not compact, but is also useless. I mean, there is no point in using that. A space is homomorphic to the Cantor space exactly when it is lambda Polish, perfect, and with dimension 0. Okay? Stop. You don't need anything else, which is, I think it's, well, a nice difference, okay? Still, it's a good result. Okay, and the last condition can be replaced by many other conditions. So, for example, that it's everywhere of weight lambda. So, in every open set, the space is of weight lambda, and also other conditions talking about discrete subsets. And also, this gives a canonical form for zero-dimensional spaces. If you take a zero-dimensional space, you can decompose it exactly as the Cantor space plus some open set of size less or equal than lambda. This is a bit strange because in the classical case, the perfect kernel of a zero-dimensional space can assume different shapes, and here it's always the Cantor space for some, well, for this result. Okay, and then let me mention, to finish this part, we went on, we studied the losing separation theorem, and this works. This works in this case if you have two analytic sets, well, lambda analytic sets, you can, which are disjoint, you can separate them with the lambda Borel set. Therefore, Borelness is the same as being B-analytic, just as in the classical case, and you have all the consequences. So a function is Borel if and only if its graph is Borel, and injective image of Borel sets are still Borel, and so on and so forth. Okay? So this part again works well, and actually again it's basically with the same proof. There's no new argument here. And then we move to the perfect set property. So perfect set property in this situation means that the set either is of size less or equal than lambda, or 2 to the lambda embeds into it. Then you can add maybe embeds as a closed set or some more condition. Okay? And what's the point here is that you can prove, mimicking the classical case directly, that every analytic set, even if the space is not 2 to the lambda, is any Poly space, every analytic set has the perfect set property. Okay? And now you can go to more important results, and you can connect, for example, with the study of I0, I mean the space V lambda plus 1 with I0. So essentially, Kramer proved that under I0, all subsets of V lambda plus 1, which are definable, so in L of V lambda plus 1, have the lambda perfect property. This maybe at first glance look like a technical statement about V lambda plus 1, but we know that they are all Borel isomorphic, so now you can just take it and move it to all the other spaces. For every space, if you have large cardinal, this large cardinal, you have the perfect set property for all definable sets, in particular, for example, for projective sets. This is the thing that I'm hoping to find out. I mean, taking some part where we have this kind of result and transfer them to this larger class of spaces. And finally, I mentioned also the silver dichotomy. Okay, this is new. This is a new result. With De Monte and Xi, we proved that if lambda is a limit of measurable cardinals, then silver's dichotomy holds. So if you take a co-analytic equivalence relation, either it has less or equal than lambda many classes, or there is a lambda perfect set of E inequivalent elements. And again, why this holds for all polyspaces, for all co-analytic equivalence relation? Well, because you have a transfer argument with all what we've developed so far, right? So you take this continuous bijection, you pull back the equivalence relation E onto the lambda to omega, which is the generalized Cantor space. Then, this is the difficult part, you prove it for the generalized Cantor space, which is combinatorially better, and then you just take it and push it forward to the other space. Okay, so developing this kind of theory could really help in spreading results on different spaces and not just on the one we are used to. Okay, let me now move to the other extreme. Okay, we dealt with countable cofinality, now we move to the regular case, that for me is the other extreme, of course. So here there is a paper by Koski-Schlicht on Fundamenta from 2017, and then we continue a bit with Philip, some work on this. So here was the setup. Now the cardinal is regular, okay? And we are assuming 2 to the less than kappa equal kappa as always. And this is the usual condition. The conjunction of the two is kappa to the less than kappa equal kappa. So we are doing this kind of generalized descriptive set theory as Yuko, Sai, and many other, including me, were doing. Okay. Now, what can we use here? We cannot use metrizability, okay, because kappa is regular, it's uncountable, doesn't have countable cofinality, therefore, and so metrizability is out of question. So we rather use a characterization of polyspaces, a different characterization of classical polyspaces, which is, if you have a second countable case, then it is Polish if and only if it is Hausdorff, regular, and strong Choquet. So 2 as a winning strategy in the strong Choquet game. Okay? So what one can do, well, we keep the characterization as a definition, so Hausdorff, regular, and then we generalize the Choquet game to this case of kappa instead of omega. So here the idea is that instead of having just omega many moves, as in the Choquet game, we have kappa many moves, okay? The game is played as before, so the first player plays an open set and a point in it. The second player plays another open set contained in the first one and contained in the point, and they go on this way. Okay? What's the difference? The difference is that when you reach a limit level, of course you make an intersection of the open set. It's not clear that you get an open set anymore. If the space may have a low additivity, it's not clear that it's kappa compact, so maybe the intersection is not an open set, but okay, one just take it as it is a subset. So what you require is that the two sets are open relatively to the intersection of what you get. Okay, so just as a subspace. Okay, so you just forget that it is not open. You continue to play open sets in this space. Okay, and the condition is the same, except now the game can die out also at limit levels before kappa, okay? Because maybe they play and the intersection is empty, and if it is empty, player 1 cannot play the point inside, okay? So player 2 must ensure not only that in the end the intersection is non-empty, but that it's non-empty everywhere, at all limit levels, okay? But it's natural generalization. This is due to Koski-Schlicht. And then you have your definition, they call this strong kappa Choquet, so they don't call it like kappa Polish or something. Okay, strong kappa Choquet for them means Hausdorff, regular, base of size kappa, and 2 wins the game. So it is strong kappa Choquet in this sense, that 2 wins the game. And again, you find your generalized Cantor space, the generalized Baire space, but also other spaces, like if you take 2 to the kappa with the lexicographical order and the topology generated, this is still one of these spaces. Okay, going on, you define objects in a natural way, so Borel sets are kappa plus Borel. Analytic sets are, again, continuous images of strong kappa Choquet spaces, or continuous images of, let me point out just a tiny detail, continuous images of closed subsets of kappa to the kappa. The difference here is that you don't have retraction in this context, okay? So you cannot move from closed set to kappa to the kappa using a retraction. Actually, these form different classes, so it's important to keep this closed here when it is regular, okay? This is something that Philip proved with Sun. Okay, and then you go on with the closure properties. Let me just list what they got actually. They got that continuous open images of strong kappa Choquet spaces are strong kappa Choquet, just as in the classical case. And here you have closure under disjoint unions of side kappa and also under products of sides kappa, okay? Because now the cofinality is kappa, so you can do this long product. One thing that you lose in this situation is that you don't have any reasonable closure under subspaces. So open subspaces are fine. An open subspace of a strong Choquet space is strong kappa Choquet, but there are also strong kappa Choquet which have arbitrarily high complexity. So they need not to be G delta or anything like that. They can be arbitrarily complex. And also you can have very easy set, like closed sets, which are not strong kappa Choquet. So there is no relation between complexity and being or not kappa Choquet. Okay, so this is something that is lost. But you keep all the other results, well, some of the other results. So any kappa Choquet space is still a continuous image of a closed set, of the bare space, and the image is Borel. You can still prove that there is a surjection, but now you need a different proof because you don't have retraction, so this must be proved separately. It's the second theorem, okay, proved from scratch. And then you have also the same situation for Borel sets. So you recover all the results maybe with different proofs. Okay? And then what about perfectness? Oh, sorry, this should be just lambda perfect. Lambda move perfect is later. Okay, so here kappa isolated, well, the right notion turns out to be the following. A point is isolated if you can isolate not just in the topology itself, but taking intersection of less than kappa many open set. So it's like closing the topology under less than kappa intersection and looking at being isolated in this other context. And then you define perfect set and perfect spaces in the usual way. And then what you get, what they get, Samkowski and Philip Schlicht, they get that if you have non-empty kappa perfect strong kappa Choquet, then you can embed the Cantor space inside. Okay, so still you can go there. When I mean that this is the right notion of being isolated, it means that it makes the theorem below work. Okay, with the original definition, it doesn't work. And then you have this Borel isomorphism. If you have two perfect strong kappa Choquet spaces, are kappa plus Borel isomorphic. Now, these are not as good as I wanted because in both cases you are keeping the condition of being kappa perfect, okay? Also in the isomorphism theorem. And actually the problem is that you cannot remove that in this situation, okay? This is a feature of this definition. First of all, if you just do the perfect kernel, depends on the procedure what you get. You can get different results looking at accumulation point or Cantor derivatives. And also the main problem is that these kernels can fail to be strong kappa Choquet. So the real proof would be I take the space, go to the perfect kernel, and then embed the Cantor space inside. But to embed the Cantor space, I need that the kernel is kappa Choquet. Okay? And here the situation, you go to the perfect kernel, and this is no more, in some cases, strong kappa Choquet. And even more seriously, with my student Agostini, we found that anytime that you have any set which doesn't satisfy the perfect set property, okay, you can just modify it a little bit and get some strong kappa Choquet space of the same size of A, which still doesn't embed the Cantor space inside. Okay, so anytime that you have a violation of the perfect set property, then you have a space which is a bit strange. I will not give the proof, I will just give the construction. The idea is that you take A as a set of binary sequences. Now you add inside the binary sequence of A, add finitely many twos, number 2 inside, okay, randomly, but just finitely many. And then you add also all sequences that have omega many 2 occurring, but after this omega many, they have also only 2, okay? So this is the idea. You just modify in this way the set A, and then add these points which are completely isolated in the space, okay? And it is easy to see that this is strong kappa Choquet.
I don't quite understand it. So you have some sequence of length.
Let me go backwards. Let's start with A. I go backwards and construct this set. Take A. Look at all the sequence inside A. Now, take all the possible sequence that you get when you add just almost binary, means finitely many occurrences of 2 in the string. Okay?
You continue the SIs before you put those 2s. That's my step.
In the second case, no. Yeah, okay, so this was the first part, and then you add isolated points. The point is that since you have just finitely many, when you have infinitely many 2, omega many 2, you are out of the space, of the previous space. And in that point, you add just one isolated point, okay, all 2s. That's the idea. So this is strong kappa Choquet just because player 2 can go in this part of the space, okay? Can play many 2s, and after omega many rounds, he will be on the isolated point, so player 1 has no choice, and he wins. So it's strong kappa Choquet for a trivial reason, essentially. And the thing is that, well, this is more difficult. One can prove that 2 to the kappa embeds into this modified space if and only if it embeds in the original space, in the original set A. So if A was not embedded in 2 to the kappa, also this space is not embedded in 2 to the kappa. Okay. So what about dimensionality? Okay, here in their paper they were really considering zero-dimensional in the inductive sense, so base of Kloppen set. Okay. Notice, however, that this is equivalent to covering dimension 0 if the space is still kappa additive, means that the topology is closed under less than kappa intersections. So this is the case, for example, for 2 to the kappa. Okay, 2 to the kappa is zero-dimensional in both cases, but they went for the original definition, except that in all the results, they were always adding kappa additive. So I think that in a revision of the paper, they should really go for the covering dimension because it's what they are doing. I mean, adding kappa additive is what makes you pass from the usual dimension to the covering dimension. Anyway, what they can prove is that if you have kappa additive strong Choquet space of dimension 0, then it is homomorphic to a subset or closed subset of the generalized Baire space. But they didn't found, and I don't have any idea on how to find a characterization of the Cantor space. So this is different, okay? The zero-dimensionality, kappa additivity, kappa perfectness are not enough, and actually me and Philip proved that there are 2 to the kappa many pairways, non-homomorphic spaces with all these features. So it's clear that this is not enough. We have to find the right conditions, but we didn't yet succeed. And now here starts the nightmare. If you go on, then if you can go for the Lusin-Suslin theorem, kappa perfectness property, or whatsoever, then nothing basically works. So you don't have separation, you don't have this Lusin-Suslin theorem, these are simply false, and essentially all other results are either false or independent from the usual set theory. Even for basic set, I mean, Sandra Müller showed you that even having the perfect set property for closed set can give you a lot of strength in the cardinal that you need to have. Of course, this looks like a nightmare for classical descriptive set theories, but it's a paradise for set theories because you find so many independence results and you can basically generate an infinite number of papers, just like one property, it will be just independent and you are done. Okay, I'm just joking, of course, but it depends on the point of view, right? It can be very interesting exactly because you have so many different situations. Okay, I was just taking the point of view of a classical descriptive set theory, which wants a stable bunch of results. Okay, and in the last part of the talk, last 10 minutes, I just want to present what we did continuing this project in the generalized case. So with this student, Agostini, we are actually taking care of the case of all lambdas. Okay, you have seen that there are many good things for lambda of countable cofinality, many good things for lambda regular, and our approach, okay, why don't you ask basically nothing? You start with your cardinal. Can you find a natural class of spaces where you can prove results? Okay, so let me show you what we did so far. I mean, this is last month's work, so there can be mistakes. Maybe you find better proof or mistakes in the statements, I don't know. So our setup is just, okay, you take any uncountable cardinal with its cofinality mu, but mu can be lambda, so can be regular, or otherwise smaller, and you keep this 2 to the less than lambda equal lambda, which is the condition to guarantee that 2 to the lambda is in the class that you are looking at. Now, we ask ourselves, which are the nice spaces that we can consider here? Well, of course, we still have to have regular and Hausdorff, because this was always present in the previous approaches, and weight lambda, so base of size lambda, because these are the natural thing to start with. Okay. Of course, we have to give up with the metrizability unless the cofinality is omega, which is the case already treated, but in all the other cases, singular cardinals of uncountable cofinality still you cannot ask for metrizability. And then we said, okay, strong Choquet gains are very important because they give you a sort of completeness. I mean, when you use a complete metric, you can mimic this with this strong Choquet. So this is still good, except that in the general situation, you should not go for lambda many steps, but just for cofinality many steps, so only for mu many steps. There is a small caveat. I mean, the definition, you can imagine what it is, but there is a slight difference that we have to use. Okay, is this enough? So we struggled a lot, and apparently nothing was working. I mean, we were successful in the cofinality omega, we were successful in the regular case, but nothing was working in between. And the point is that actually Claudio, my student, found out that there was a somewhat missing condition, which was really hidden. And the condition is this one. Say that the space is mu Nagata-Smirnov were the mathematician who introduced this for mu equal omega. This is a kind of generalization. So mu Nagata-Smirnov means that you have a base, but the base can be stratified in mu many levels, so cofinality of lambda many levels. And now, if you look at a single level, it must have this property, that if you take a point x and fix the level I, then there is at least one neighbor of x in the topology, such that in that level, only less than mu many open set intersect this neighbor, okay? So for every point, there is a neighbor, and this neighbor touches only few sets in its own level. And of course, if you change the level, you will have to change the neighbor and whatsoever, okay? So this appeared to be a strange condition, but why Nagata-Smirnov introduced it? Well, because this is actually a characterization of a metrizability for arbitrary spaces. A space, topological space X is metrizable if and only if it is Hausdorff and regular, as usual, and it is omega Nagata-Smirnov. So you have this base in omega many levels. So why we didn't see the condition in the countable cofinality case? Because it was already in the metric, okay? The metric was already doing the job, so you don't see this condition. But also, we couldn't see in the regular case, because if lambda is regular, any space of weight lambda is lambda Nagata-Smirnov, because the levels are just singleton. You have just lambda many basic open set in the base, so you treat them as one level. Each of them is one level, and you are done, okay? So you can cheat. So that's why you cannot discover this notion working with these extreme cases, and it shows up just in the middle. And here, oh no, there is one more thing to come to the definition, which is essentially the final thing, except a list of results. About strong Choquet gains. The problem with strong Choquet in the regular case was that the perfect kernel was not working. So you have a strong Choquet space, you go to the perfect kernel, maybe it's not strong Choquet, and so you cannot embed the set, okay? So we try to fix it with a variation of the game. So the game is exactly as before, okay? It runs for cofinality of lambda many steps, but now you require that all sets played are open relatively to the intersection, but of size at least lambda. Okay? So they cannot be too small. You cannot concentrate on isolated points. Okay? And then you say that 2 wins the game if the game doesn't stop before mu, which means when you do the intersection, what you get is a space at least of size lambda, because otherwise one cannot play anymore. And as usual, the intersection is non-empty. Okay, so we had to modify these two things, add the Nagata-Smirnov condition, plus modify the game of Kostky-Schlicht, actually the Choquet game. And Yeah, and now with all of this, we have this definition. I write tentative because essentially we are trying to find out the right definition, prove theorems, and then maybe we revise the definition. If it doesn't work, we try to understand what's going on. But for now it works, so I hope it will continue to work. I call the space lambda descriptive set theoretic. This means it works for descriptive set theory. I don't want to use Polish because maybe Polish is completely metrizable of certain density, so I just change the name. So what means descriptive set theoretic, so good space? Well, base of size lambda, regular Hausdorff, Nagata-Smirnov, mu Nagata-Smirnov, plus 2 as a winning strategy in the variant of the Choquet game. Okay? You put all them together, and this is the Choquet space. Actually, this is very close to to Polish definition. Polish definition is base of size omega, metrizable, and actually completely metrizable. And here you see, wait, metrizability, this is an analog of metrizability, and completeness. Okay, so you are really asking the right generalized properties. Okay, then you go on defining things in the usual way. So Borel sets are unions of side lambda, intersection of side lambda, closure under this operation. Analytic sets defined in the usual way. What you get? Okay, closure properties is essentially as before. You are closed under disjoint union of size lambda and products just up to the cofinality. Okay, this is the natural thing. You don't have closure under subspaces as in the regular case, and except for the countable cofinality case, because there you have the complete matrix, so you have this closure under G delta, but except for that case, you don't have closure under subspaces, essentially. You save essentially the result we saw before, so every space is still a continuous image, injective image of a closed set with inverse Borel. Still, you can modify this to a surjection from lambda to the mu. Still, the same is true for Borel sets. So I'm just listing, these are always the same result, but this works in this very, very general setup now. And then what about perfectness? Of course, we have to change again the definition of isolated. And what we did is just the Cartesian product of the first two. The first one is open set, well, isolated means open set of small size, less than lambda. The second one, isolated in the real sense, but taking intersection of size less than mu instead of open sets. And now it means, isolated means intersection of size less than mu and of size smaller than lambda. If you end up in such a set, then you are isolated. It's exactly the Cartesian product of the two. I mean, it's the natural thing to do. Then you need to define what is a perfect space. That's the usual definition. And then now you can again prove the same result. Okay, the same result, which is if the space is perfect, then you can embed the Cantor space, where if lambda is regular, is the Koski-Schlick proof essentially. If kappa is singular, maybe of uncountable cofinality, then you embed always this space, and you have to check the splitting and all this stuff. This is the most complicated case. It's not as simple as the cofinality omega. It's not as simple as the regular case. It's really something new, but it works under our condition. Okay. So essentially what we did is combine the techniques in the countable cofinality case, regular case, and let me mention that here is where you see that mu Nagata-Smirnov is necessary, because when you are in between the cases, so cofinality is not countable but not lambda, so it's not regular, the crucial thing is having this mu Nagata-Smirnov property, okay, to make the proof work. Okay, 2, 3 minutes? 2, okay. Now, the good thing is that with this definition, modified Choquet, you have the decomposition in a perfect kernel and the rest, okay, even in the regular case. Why now it works? Because we modified the Choquet game, okay? It's the modification of the Choquet game that in the regular case resolved the problem that we had before. And it's important, the important thing is that with this definition we get a perfect kernel, descriptive set theoretic kernel, so still in the class of spaces. Okay, and therefore you get that you have CH, topological CH for this class of spaces, even they are small, or you can embed the Cantor space. You have the Borel isomorphism theorem. They are all isomorphic provided they have the same size, and you can go on. So, in the last minutes, if I can, this is what we have so far, okay? There is more to be done. Let me compare with what happened before, okay? So, if you take the regular case, we have a different definition from Koski-Schlick. But our definition is not in the Nagata-Smirnov condition. This was for free in the regular case. So in that case, we are not adding anything. And also, we are not changing the definition of isolated and so of perfect. If you apply our definition in the regular case, you exactly obtain the definition of Cauchy-Schlicht. I mean, you have to prove it, but you get the same notion, so we are not changing too much. But in general, our class of spaces is a proper subset of the class considered by Cauchy-Schlicht, okay? And in a strong sense, I mean, there are spaces which are strong Kappa-Choquet and they are not even lambda plus Borel isomorphic to our spaces, okay? So they were considering more spaces, but if you just work with perfect spaces, then nothing has changed. So the point is that they had problems just in this part of the isolated points, and we managed to solve it essentially. On the perfect case, it was already the good definition. Okay, and actually our definition is okay because if you start with any space and found that the kernel is descriptive set theoretic, then the original space was descriptive set theoretic. So you cannot change it. I mean, this is the right definition, the definition we have. In the countable case, our spaces are close to completely metrizable spaces of size lambda, essentially because again, Nagata-Smith is for free and everything is much closer. Okay, and I will just let the last slide. Coming soon, what we are doing now, well, we worked for 1 month in finding the right definition. We proved the first theorems. Of course, now we have to go for all the things that you saw in the other cases. Okay, a lot of work has been done in the countable cofinality and regular case. We want to do the same for this general setup. So consider zero dimensionality, probably covering Lebesgue covering dimension. We want to find the characterization of the counter space if we can. We want to work with perfect set properties, Silver's dichotomy, whatsoever. Okay, we don't expect to have always this is true, but okay, at least to find out the right condition whether you get independence or the theorem is true. Okay, and then we want to find application elsewhere. This was the main goal. Okay, we developed this general theory to tackle classification problems elsewhere for non-separable spaces or uncountable structures. And most notably, I would really like to find interaction with other fields, because basically, we are dealing with many things that appear in combinatorics. So for example, if you do PCF theory, you are working with subset with product of the lambda I, but product of the lambda I is our space. So maybe if you add definability, you can get some more result observation or you understand a little bit more. I don't know. This is my hope, but I'm not sure that it works. Thank you for the attention.